Good morning. This is lecture 10, and we're going to be discussing the concept of force transmission and transmissibility in general today. So here's the agenda for today. First of all, we started the subject of a mass spring damper system under harmonic load last time. And the base was stationary. In other words, the one end of the mass, one end of the spring and the damper was attached to the mass, and the other end was attached to a ground or a base that was sitting put. It was not moving at all. Once we already started that, and I came up with a bunch of expressions for the let me see now, the displacement of the mass. And what we like to do today is find out come up with an expression for the forces that are transmitted from that oscillating mass through the spring and the damper to the foundation, to the ground. Okay, and then we're going to assume that the base or the ground is also moving, in fact, moving harmonically. And what we like to do is to come up with equivalent expressions that we did in item number 1 and the lecture prior to that for such a scenario, a moving foundation or basic excitation. So that's item number 3. And finally, we start the subject of rotating unbalance, where again, because of the unbalance in a machine, for example, there is a harmonic load that is applied from the machine into the foundation. So essentially, these things, base excitation and rotating unbalance, they're special cases of the uh, uh, system under harmonic loading. Okay. All right. Let's do a quick review of what we did last time. So we have a mass attached to a spring and a damper, attached to a fixed foundation. Now this mass is under a load which has a very special kind, namely a harmonic load, F naught cos omega t. If f of t is a general description which doesn't fit this, then we have to wait until chapter 3. So this omega that you see in the solution, and the solution that you see here is the position of this mass as a function of time. So notice that what it's saying is that if the load is oscillating uh, with the frequency omega, the solution or the steady state solution also is oscillating with the frequency omega. But there is a there's, there is a lag, and as long as we have a damper, this lag is there, and there is an amplitude that we discussed last time on how you get it. And we're not going to go through it, but the expression for x was given, and on the right-hand side, it depended on, of course, the F naught, the static loading or the amplitude of the load, and depended on the stiffness and damping ratio, etc. The big thing is that x itself dependent on what is called the magnification factor. So anyway, we'll get together. We're not going to go through it, except that I want to remind you that this was done on Thursday of last week. Yeah. So what we want to know is what is the force transmitted to the ground. Now, the force transmitted to the ground, if you think about it, is just the force that's coming from the spring and the one from the damper. Force of the spring is always the stiffness of the spring times the amount of stretching or compression. And because the base is fixed, that compression or stretching is just xp, the position of the mass, basically. Now, the damper is Cx dot P, in other words, the velocity of the particle. Now, particle meaning mass. Now we have the expression for xp. It's right over here, and so we can just plug these things, plug that expression into this, and do a little bit of algebra. So the derivative of this expression is just omega times the negative sign of omega t minus phi times x. So there we are. This is it. This we just wrote multiplied by k. This one we just differentiated the expression for xp and plugged it in there. Now, because there is a cosine of this angle and the sine of the same angle, we can actually go ahead and find the magnitude of transmitted force. Because look, just look at it. Transmitted force is a function of time. It changes with time. And it's made of these two sines and cosines, which also themselves vary with respect to time. If these frequencies are the same, or these angles are the same, omega t minus theta, then you can say that this uh, expression for uh, transmitted force, which is itself a sinusoidal, has an amplitude which is the square of this plus the square of that. Okay? And in general, if these two angles are different, which is not the case in our situation, but if these angles are different, you cannot just say that uh, the magnitude of the transmitted force is the sum of the square of these two. But because these angles are the same, this is perfectly legitimate. Now, what we're going to do is, based on the stuff that we did on Thursday, we're going to try to rewrite this in terms of not omega, but in terms of the frequency ratio. So basically what we did, factored factored the k out of this expression and just kept in mind that every time we saw a k over m, it is omega n squared. Okay, every time we see a k over m, that's omega n squared. And we have the expression for c in terms of the critical uh, uh, frequency ratio and the critical damping. So basically, after a bit of algebra, you get this. I mean, basically, you take the k out of that, okay? X is already here. This X is already here from Thursday's lecture. We take the K out of that. Now these K's cancel. And this thing, if you look at it carefully, what you have here is, uh, uh, if you look at this expression, the top is Km divided by K squared. So one of the k's cancel, you have m divided by k, because this k, after you square it, cancels one of these. And m over k is just 1 over omega n, or k over n is just omega n squared. That's what I really meant, okay? So if you simplify this thing, it's going to be m over k, which is 1 over omega n squared. And notice that we have omega squared over omega n squared, so that's how you get the r there. Basically, algebra is going to give you this, okay? So the transmitted force changes with time. We know that. But it changes with time and it varies sinusoidally, okay? And the amplitude, as soon as it says sinusoidally, it has an amplitude. The amplitude of it, which is the maximum value that it can take, is simply that expression. You give me the amplitude of the load and give me the R frequency ratio and zeta, I can tell you what is the maximum force that's going to get transmitted to the foundation, to the ground. This ratio, if you look at the FTR, which is the maximum transmitted force, divided by F naught, this is the amplitude of the harmonic force that is applied, is called force transmissibility. Very frequently, the force is left out of that. They may call it transmissibility depending on textbook, but anyway, I would like to avoid confusion, I would like to call this thing force transmissibility. And the reason I do that is that when we do the next subject, namely the issue of the base excitation, we have a force transmissibility and we have a displacement transmissibility. So that's why I would like to, as much as possible, keep them distinct. But right now, never mind about this displacement transmissibility, doesn't apply to the present case. It's just force transmissibility that uh, uh, comes in the picture. Now, force transmissibility is also referred to as 1 minus base isolation. Okay? So if you tell me that hypothetically, if you tell me that the force transmissibility is zero point 0.6, then the isolation, base isolation is 40, 0.4. Okay? To say that this is zero point 0.6 means that uh, only zero point 0.6 of the applied amplitude is going to get transmitted. Okay, so this is what I just said. Force transmissibility is 1 minus base isolation, or percent force transmissibility is 100 minus percent base isolation. Okay, here I've written the same thing except that I left force and base out of it. So let's do an example. So suppose Suppose we have a block sitting on the ground, on the stationary ground, no isolation. You apply a force on it. That entire force is going to get transmitted to the base. In other words, the base, the foundation, the ground will actually see F of t. However, from everyday point of view, you know that if you put this mass on a soft cushion, for example, uh, less force is going to get transmitted, right? So that's what the idea of isolation is. Base isolation is, ground isolation. So what you do is you mount this thing on a spring and a damper, properly designed, so that the entire force is not transmitted. Okay, and I just showed you how the formula works. So we're going to do an example here. So here, the mass is 100 kilogram, and if it's sitting on the ground and a harmonic load is applied, the entire force is going to get transmitted. But we mount it on an isolation system, or a mass and spring and damper. So the idea is to design this, in other words, come up with a KNSA, which meets two requirements. Number one, when the operating frequency is 4 hertz, when this is on the sinusoidal load 4 hertz, by the way, don't let this thing bother you, because this can be sine or cosine. It really doesn't matter. Everything is going to be the same thing. But when the frequency of the applied load, omega, is 4 hertz, we have isolation of 40%. And at resonance, that's the worst case scenario, we want the transmitted force to be not more than twice the applied amplitude, applied force. Okay. So first of all, we are told that as part of this requirement, 40% isolation, we are told that percent isolation is 40% or zero point 0.4. Therefore, transmissibility is just 0.6. Just keep that in mind. We know that this requirement has to be met. The other one is that when we are at resonance, Ft, Ftr over F naught should be 2, not more than 2. Let's put it this way. At resonance, where omega and omega n are the same, the applied frequency of the load and the natural frequency of the mass spring damper system is the same. We want the ratio Ft over F naught to be 2. All right, so let's see. We start with Ft over F naught equal to 2. And out of that, when R is 1, notice that we're talking about at resonance, when R is 1, you get the value of the damping. So that requirement tells us that the damping ratio is 0.289. Now we go to the part that said Ft over F naught is uh, uh, zero point 0.6, okay? So at 4 hertz. So this was the expression. We know that We want this ratio to be 0.6. Okay, we want this thing to be 0.6. And we just found the damping ratio. And in here, we solve and we get the value of R. R is the ratio of the applied load frequency over the natural frequency. Okay, now applied load frequency is 4 hertz. We're told that it's 4 hertz. Okay, when we convert this 4 hertz to radians, it's going to be 8 pi radians per second. Omega n is right here, so we know that this ratio is supposed to be 1.7769. 4 times 2 pi, this is radians per second, this was 4 hertz, and out of that, the mass is 100 kilogram. Out of that, you're going to get your K. Once you have your K, and once you have your K, because you have your uh, oops, this is not correct. This is not correct. Okay, this should be, oops, let's clean this up right now. This is C, this is C critical. Okay, so we need to multiply that thing by psi, zeta. So let me clean this up. Oh, zeta. Okay, right there. Okay, so let's go here. No problem with K. K count comes out of that. And remember, zeta is C over C critical. This is C critical. We found zeta. We just found K. We know M, and you just work it out, and you're going to get your damping constant. Okay, so basically we designed a foundation or isolation system so that the requirements that we wanted actually was holding, namely at 4 hertz. The isolation, ground isolation, foundation isolation was 0.4, okay, 40%. And at resonance, the ratio of Ft over F naught, the maximum transmitted force ratio was 2. So, okay, good. Now, we are done with the first part of this chapter, which is a mass spring damper system under a harmonic load. Now, as an application of this, we have the following two problems, okay? The following two class of uh, subjects. One of them is base isolation, and that's what we're going to do that. Or not base isolation, sorry, base excitation or base movement. So very often machines or components are sitting on foundation that are themselves moving, okay? And very often they're harmonically moving, okay? So an example is that suspension system of a car. So here's a mass. It's sitting on through a mass spring damper system, obviously. You know that you will need suspension. It's sitting on uh, it's moving on a, let's say, on a road like that, okay? So the base, this massless base, this is the base. See that? This thing, we are assuming the mass of it is much smaller than mass of the car. This, no mass, okay? This is moving in a certain way, and for example, a harmonic wave, a harmonic type of variation. Uh, yeah, so we want to solve this problem. Okay, so first thing that we're going to do is to come up with the appropriate equation. Here's the base. Remember, think about this thing as the suspension of a car moving on a road. Think about it like that. Okay, or think about this on a machine which sits on the ground, and the ground is ice. The ground is moving because of something else moving next to it. Okay, so the motion of the base, we are assuming that we know y of t, and because the base is moving, the mass is also moving, okay, by the amount x. So if you draw the free body diagram of the mass, what are the forces that are acting on the mass? Well, there is the spring force. But remember, spring force is not just kx. It's because mass is moving by x, base is moving by y. The stretching or compression of that spring is just x minus y. So the force on that mass is k times the amount of stretching or the amount of compression, x minus y. And the same thing with the damper, because the mass has a velocity, the damper has the base has a velocity. So the velocity that the damper sees actually is the difference of these two, x dot minus y dot multiplied by the damping constant, and it's going to be force. So write down sum of all the forces equal to mass times acceleration. And this acceleration that you see is acceleration of the mass block. It's from some reference equilibrium position. Okay, so we can use Newton's second law. Okay, and this is what we get. So sum of all the forces, these are both negative because these are in opposite direction, equal to mass times acceleration. Bring everything to one side, you're going to get this. Now we know that y of t, the base, moves with a certain prescribed uh, uh, form. So let's assume for the sake of this chapter or elementary stuff that we're doing in a vibration, it is actually moving with some amplitude harmonically, okay, sinusoidally. So this omega sub b is the driving frequency, which is because of the motion of the base, and y is the amplitude of the oscillation of the base. Okay, now uh, big Y is the amplitude and omega B is the driving frequency. So we're going to take this and stick it up there. We're going to take this Y and put it up there because there's nothing unknown about this Y. Everything we know, we put it up there and we clean up. We're going to get this. Mx double dot plus Cx dot plus Kx equal to a right-hand side. And the reason the right-hand side looks like that, because there is a y ends up on the right hand side, and y basically has a y and it's a sign, it's this thing, and obviously it's multiplied by k, and there is a y dot that ends up on that side, so there is your y dot that ends up on the other side, multiplied obviously by c, etc. Now, and of course you have to differentiate this. You're going to get cosine with a negative with a cosine with omega b in the front. Okay. Now, this looks familiar. It's ugly, uglier than what we already handled. Before, we handled the stuff on the right-hand side was some constant, let's say F naught, times cosine of omega t. Now, you not only have, well, first of all, F naught is this, and you not only have cosine, you also have the sine, and etc. So, what we do is the following. This is a familiar thing. We recognize this because we have done problems like that, except that this thing was called F naught. Now, there is this extra term, so let's go and see how we handle this. We can think about this. There are two ways of doing it. One way is to say that, oh, we have two problems actually. One with the first term on the right-hand side, and then another one with the second term on the right-hand side. Each one of these are just constants. Cy omega b is just a constant, and ky is just a constant. Each one of these we know how to handle. In fact, we have done this thing many, many times last week. Okay, this one is the same animal except that it's a sine. Okay, but fundamentally nothing is different. So out of that we get an x1. Out of that we get an x2, and we have to add them up because of superposition. We say that the solution to this equation is actually solution to that plus the solution to this. Each one of these individually, if we wanted to, we can get it. And if you add these up and do some elementary trigonometry, you can write it like that. This is not rocket science. Or maybe it is, I don't know. Uh, Notice that when the right-hand side was cosine, we ended up with cosine and some phase angle. Here we have two phase angles, one for that and one for this. That's why we get this, okay? And theta 1 is like so, and theta 2 is like that. Look, somebody has done the dirty work for us. This is not hard. This is, you just have to do it. If you know where it's coming from, you just have to sit down and work it out. There is no intuition, there is no physics, you just have to work it out. So here's what happened. Let me go back here. Notice that the solution of the displacement of the mass, this is very important, displacement of the mass is also cosine of omega bt. That's not surprising. The amplitude is ugly. It's right here. Oops. The amplitude is ugly. It's right here. And there is a phase. Okay. So the amplitude of this xp, which we call big X, remember, big X is the amplitude. Big X is the amplitude of little xp. So there we are. Now notice that if you go back, let me go back one more time. This has omega and omega b and omega n in it. We did some work. I showed you that it's better, it's easier, and more readily understandable if you factor omega n squared out and you have things like omega b over omega n, which is r. And we have done this kind of thing before. Okay, so the amplitude of the oscillation of the mass is related to the amplitude of the oscillation of the base, this big Y. Remember, this was the amplitude of the base, oscillation of the base, multiplied by that. This is why in the case where the base is moving, like in our case, you can look at big X over big Y. This is the amplitude of the motion of the block. This is the amplitude of the motion of the base. So it makes sense to talk about this ratio and give it a name, displacement transmissibility. Now, in the case where the base is fixed, it does not moving, obviously y is 0. So, I mean, just didn't make sense to go and talk about something like that in the first part of this lecture, okay? Which was fixed foundation, fixed base. Now, this is called the displacement transmissibility and is used to describe how motion is transmitted from the base to the mass as a function of the frequency ratio. Okay, how motion is transmitted, that means displacement is transmitted from the base to the mass. We can also plot these things, plot these, and I want to say a few words about it. I mean, basically, these graphs say it all, but let's think about it for a second. First of all, notice that when the frequency ratio is less than root 2, right there, look at the height of these curves. They're always bigger than 1. As long as frequency ratio is less than root 2, always the block moves more than the base. In other words, the amplitude is more. Okay. Now, when you give me for a given ratio of r, the value of the damping tells you how much bigger. The higher the damping, the lower that ratio. You can see that when the damping is light, that block will go nuts and X will be very large. But if the damping is gets bigger and bigger, that ratio becomes smaller, still amplified, but uh, that ratio X over Y becomes smaller than a lighter damping case. Okay? Anything to the left is amplification of the displacement. There's no doubt about it. But As the damping increases, that ratio gets lower and lower. Now, if R is bigger than root 2, the transmissibility, displacement transmissibility, x over y, this is displacement, is always less than 1. As long as R is bigger than root 2, is always less than 1. Uh, uh, Now, of course, notice that here, if you increase damping, although it's the ratio is less than 1, but it's not going to improve that, amount of the value of the ratio. It actually gets worse. Okay, you can see that. All right, so let's think about it. Here is you're traveling on a rough road, sitting directly on that seat. Would you feel happy? Probably not. Most probably you're going to need some soft cushion underneath you, which essentially means that you have designed a damper on an isolation system or mass or a spring damper system. Okay, and the selection of C and K must be so that it meets our requirements. For example, not too much force is transmitted. Okay, so and this is what we want to discuss now: force transmission. We're going to take a 1 minute break. Running out of breath here. Just a second. Okay, so now we want to talk about force transmission for a base excitation. Okay, what we just did was discuss uh, the amplitude transmission. Okay, the displacement transmission, not amplitude. What we just discussed was the displacement transition, displacement transmission. Now we want to talk about force transmission. Okay, so well, once again, the force is transmitted through the spring and the damper. Okay, so force is equal to K times the amount of stretching plus C times the difference in velocities. Okay, now uh, because there is no other force, this f of t must be mass times acceleration. You know that because just look at the problem that we're solving. That drawing that I had a minute ago. That for example, person or a car going over a rough surface. There is no force acting there. Okay, external force. So basically, the only force is that the inertia or mass times acceleration. So the moral of the story is that this thing, this thing, okay, is minus m x double dot. We already know that. Now, uh, we already found x in the previous slide. Okay, we already found it. It was ugly expression, something that people have found for us. And x dot, you can differentiate it. Okay, and then you plug it in here and do the algebra. You're going to come up with that expression. Look, we already got xp. Remember how I got xp of 1 plus xp of 2? And I said, this brute force, you have to do it if you want to know why. Somebody has done it for us. Take that x, differentiate it, stick it in here, and do the algebra. Okay? The easier way is to recognize that f of t is actually mx double dot. So you already have that ugly expression for xp. Differentiate it twice, and you get this expression. So this observation, and because there is no other force acting, which means that no other external force is acting, this f of t must be mass times acceleration. We already found x. We called it xp of t, but we already found it. Somebody has found it for us. And you differentiate it twice, you're going to get cosine back. Remember, this thing was cosine omega bt. There was a theta 1 in it and a theta 2 in it. You remember that? If not, go back please and watch it. And there was an amplitude there. So if you differentiate that expression twice and stick it in here, you get f of t for free. You don't have to worry about this because this is actually telling you that f of t is minus mx double dot. Anyway, so here's the story. This whole thing in the front is the amplitude of the transmitted force. This is the actual force transmitted to ground. Multiple, of course, it has a cosine in it, so this must be the amplitude. This whole thing must be the amplitude. I don't particularly like it because it had omega n in it and omega b in it. Remember, we like things in terms of r. So actually, if you do the algebra, rewrite this in terms of r, this is what you're going to get. Again, this is strictly algebra. All he has done, the author has done, is that every time you have omega b, you write it as omega b over omega n and see what you can take out. And uh, I mean, if you do that, you're going to come up with this expression. Now, a couple of things here. Notice that when we did force transmission in the when I started this lecture today, I assumed that it's a harmonic motion, and we did the solution to that on Thursday. But today we did the force transmission for that, and we got this expression. This expression is what we had as force transmission ft over f naught. Okay, we had that. When you have a moving base, then there's a constant. You can think about this in alpha, but there's also r squared. So this form is a little bit different from what we did earlier today. However, it's derivable from that, but I'm not going to do it. Okay. So we will try to keep these separate so that you know when you're moving with a, base excitation, what is the expression for Ft. I don't want to mix it up with the previous situation where the base was fixed. Okay, now if you divide by Ky, incidentally, think about what is Ky. K is the stiffness, right? And y is the amplitude of the base. Okay, so you can think about this thing as some kind of a force. Okay, uh, you can think about it as some kind of a force. Okay, so this is called force transmissibility, but it is for a moving base or base excitation. Okay, and there's an r squared here. In the first part of the course, the first 15 minutes, we had ft over f naught, and there was no r squared there. Okay, so let's move on. You can plot it. So this is the plot of that same curve that I showed you as a function of r, and it's not as nice as you would have expected. There's a few things that you can observe here. This force transmissibility ratio expresses a dimensionless measure. This is a dimensionless quantity. That's why we picked on Ky, so that this becomes dimensionless, of how the displacement in the base amplitude y results in a force magnitude applied to the mass. So Ft, remember, Ft is the force coming to the mass. You're sitting on that hard surface as it's moving on a rough road. Okay, you feel Ft, and you're feeling it because the amplitude, the base, the road is rough. It moves up and down. Now, one thing that you notice here is that xp, if you look at the expression for xp, I'm not going to back up because it just makes people go dizzy. Expression for xp and expression for ft immediately in the previous slide, they have exactly the same type of thing as the argument of cosine. They're both cosine of omega b which is the base driving frequency, omega b times t minus theta 1 minus theta 2. So they are in phase because they both have the same cosine of same angle. Okay, and yeah, it's right here. That's wrote it. Slides 9 and 13. That's why I said I'm not going to go back. Both xp and f, as function of time, both involve this. They are in phase. Okay. Now, remember that for r bigger than root 2, the displacement transmissibility was less than 1, but that is not the case here, and it doesn't fall off. Okay, if you go to the previous slide, one of the previous slides, maybe 2 slides ago, it was x over y, big X over big Y. For r bigger than root 2, actually, they were all below the line height of 1, but that is not the case here. Okay. So these formulas are useful for designing, cushions, basically, spring damper system to reduce the force transmitted to the occupant of a car. We're going to do an example here. Okay. So let's look at a road. Approximate the road as a sinusoid from peak to peak or from a trough to trough is called the road wavelength. And of course, this height is twice the amplitude of the road. Okay, so because this is double the amplitude. If you look at this thing as a sine curve, this is double the amplitude. Amplitude is just half of that. All right. Now, first of all, we want to model this thing. For example, we want to know in a particular problem, the road is going up and down by that much. How much does the occupant go up and down? In other words, big X. We want to find big X in terms of big Y, and big Y, by the way, is half of this. Okay, 0.01 right there. And then we want to know how much force is transmitted. Okay, so determine the effect of the speed on the amplitude of displacement as well as the mass of the car. So we want to know, first of all, how the speed changes things and how the mass changes things in terms of displacement of the occupant. Now we are assuming that the stiffness of the spring and the damping constants are given by these numbers. Let's start with and take the mass of the car to be almost a ton, 1,007 kilograms. This is a small car, very small car. So let's rewrite for your assistance the mass of the car, damping coefficient, stiffness of the spring. So first of all, let's think about this for a second. If the car goes very fast, if the car goes very fast, high speed, do you agree that this wheel goes up and down very fast? So the frequency where this oscillation is taking place, oscillation of the base is taking place, increases with increasing the velocity. If you go over this thing very slowly, the frequency is very small also, or the period is very large. But if this goes very fast, if the car goes very fast over the road, this wheel or the suspension goes up and down very quickly, very fast. So the conversion is very easy. Basically, if you want to know the frequency, here's what you do. You find the period. In other words, given the speed of the car, how much time it takes to go from here to here? 6 meters. Okay? Which obviously you're going to take the speed divided by that distance, right? Assuming the conversions are made correctly. Okay. Now that will give you the period of oscillation. And if you take convert that to the frequency, remember the relationship between frequency and period is omega equal to 2 pi over t. Frequency equal to 2 pi over the period. So period is going to be 2 pi over omega. Okay. So anyway, you plug it in you plug in all these things, and you're going to get this expression. So the frequency of oscillation of the suspension, think about it like that, is 0.2909 times the velocity of the car in kilometers per hour. All the conversions were done here. If it goes 20 kilo, if it goes v at v kilometers per hour multiplied by 0.2909, you're going to get the frequency of oscillation of the foundation or the base. Okay, all right, that's what this 6 is. Now, remember, this is 2y, so big Y is actually just 0.01. Now, let's take the case where the car goes at 20 kilometers per hour and work it out. The frequency of oscillation here is 5.1 radians per second. The natural frequency is going to be square root of the stiffness of the spring divided by the mass of the car, 19.93. And you find the frequency ratio, which is the driving frequency, omega b, divided by natural frequency. Remember, the only reason I put a subscript b here, because this is, we're talking about base excitation. I mean, you don't like it, you don't want to leave it out, you can do that too. Now, you have the value of c, you have the stiffness of the spring and the mass of the car. You can find uh, uh, the damping ratio, which is right here. And now you go and stick it in there. Big Y was 0.01. You just found psi. You found the uh, frequency ratio. You plug it in. You're going to get your X. If this is 1 meter, right? This is 1 meter, 0.01. This is 1 centimeter amplitude of the road. It says that the occupant goes by 1.1 centimeters. Okay, so remember, uh, this cutoff was √2. What did we get for R here? Our R was actually 0.292, which is less than √2. That's why it is amplified. It is amplified. You can see that. Not by much, but it is amplified. And the reason it's not by much, because the damping is very high. Okay. All right. Now, so the suspension system amplifies the rough road bumps in this design. Now, let's look at the effect of the mass of the car. So this is the small car that we looked at, and let's look at the sedan, which is 1.5 times bigger than that. And we look at several speeds, 20, 80, 20 kilometers per hour, and we just did that, by the way, 20 kilometers per hour for the the uh, for the smaller car. We came out with 1.1, which is basically a rounded value for this 1.08. Now, first of all, you notice that uh, with higher speeds means down this road, the bigger car, the bigger car has less uh, amplitude magnification. Okay, so this is the bigger car, heavier car. Think about it like that. And notice that when you compare it to the smaller car, the the oscillation of the smaller car at that amplitude is half a centimeter. Okay, whereas for the bigger car is zero point 0.3 centimeter. Okay. Now, also, uh, if you look at it, it says the suspension system parameters chosen work better in general for a larger car, except at low speed. At low speeds, if you look at it another way up here, this is a bigger car. At low speed, 20 and 80, actually, uh, compare these two, for example. 20, look at the 20, the bigger car actually uh, uh, moves with a higher amplitude, 1.1. This is the uh, bigger car, slow speed. See, the occupant for a smaller car feels 1.1. We just did it. For the bigger car, it's a little bit more than that, 1.14. Okay. Oops. I think I hmm. Okay, I had to go and do a cleanup of this particular slide. So here's the problem. Another example of base excitation. So we have a large rotating machine that causes the floor of a factory to oscillate sinusoidally. Okay, so maybe it's sitting next to, I don't know, a compressor or something like that, or very heavy duty fan that makes the floor to vibrate. Now, a punch press is to be mounted on the same floor. Okay, the displacement of the floor at the point where the punch press is to be mounted measured to be this. So it looks like it oscillates up and down at roughly a tenth of a centimeter. What we like to know basically is how much force is transmitted to that punch press. Okay, so punch press is sitting on the ground and the ground is moving like that. Obviously, the punch press is also moving because of we just discussed, but we want to know how much force is actually transmitted to that punch press. Now, there's some information that's given to us. It says find, well, first of all, the data is here, the mass and the, uh, the spring and the damper. This is for the foundation where for the punch press is to be mounted on. But it says calculate the maximum force transmitted to the punch press at resonance if the machine is mounted on rubber fitting with this data. Okay. So basically, we have to know the expression for the transmitted force is right here. And notice that in here, we need a few things. We need the stiffness of the spring. We need the amplitude of the vibration of the floor or the base, which is 0.1. We need xi, and we need r. But we are asked to find this when at resonance, which is the worst case scenario almost, where r is equal to 1. So we know what r is here. Okay. So at resonance when r is equal to 1, we just plug these things in and notice that I just do a cleanup. It's going to look like this. Now, I have written it for your uh, perusal here. So what do we know? We are given the damping coefficient and the stiffness of the spring and the mass of the object, so we can find the uh, damping ratio. And now we can just plug it up there. Big Y is 0.1 centimeter, which is 0.001 meter, right? Just plug it in and you get 501.6 Newton. Okay, so that takes care of it. Now, there is a table in the book which is actually pretty good. It's table 5.1. If you look at the middle one, it's the first discussion that we had at the beginning of the hour. In other words, ground is fixed, the mass is subjected to a sinusoidal load like that. Okay, and don't let it bother you whether it's a cosine or sine. It really doesn't matter. Everything is going to go through if all the cosines are replaced with sines or the other way around. And uh, right, so first of all, the displacement transmissibility does not make sense. Big X over big Y does not make sense. We know that because big Y is 0. But force transmissibility makes sense. So big F, force transmitted, the amplitude of force transmitted, and F naught, the applied force, this makes sense. And this is the ratio. We already discussed this. When you have base movement, moving base, or base excitation, assuming that here it is, I didn't put a B here, but in the previous slides, I put the omega B here, base frequency, driving frequency, okay? Now here, displacement transmissibility makes sense because big X over big Y, the amplitude of the vibration of the mass divided by amplitude of the vibration of the floor or the base, this makes sense. And it's given by that. And it's interesting because this is just like this. However, when we found the force transmitted, okay, or force transmissibility ratio, there is an R squared here. R squared. There is an R squared here. Okay. And I want to remind you that whenever we have transmissibility, percent isolation is actually this is uh, yeah, okay. So as long as you interpret this thing correctly, I would rather take this thing off here instead of percent isolation. I want to say isolation. Okay, I like this thing better there. Because if it's percent isolation, percent, you just have to be careful. So, all right. So the last topic of discussion today, and we're going to continue with this thing on Thursday. We're gonna do wrap this up. Do a lot of examples on Thursday, just letting you know where we're going. This is also a case of the mass applied to subjected to harmonic load. It is still a special case, special application, just like the moving base was or base excitation was a special application. Uh, so if you see similarity, it's not as surprising because this is actually a special application. So we have here a mass, and in it there is an imbalance. A motor, for example, rotating imbalance. For example, think about this thing as a motor, and think about it as or one of the turning component in it is chipped off or broken, or on purpose, a little mass is attached to it. So when you think about it, as this thing turns, it actually insert a force up and down, also sideways. But what the vibration here, mostly that we're concerned with, is up and down vibration because that's our degree of freedom. Okay. Now, I mean, you don't have to be genius to see that to reduce the amount of force which goes through the ground, goes through the foundation, you have to mount this thing on some rubber footing, basically. You have to design an isolation system which involves a cushion or a spring and a damper. Okay? So what you want to know is what is the governing equation for this so that at some point we can design the K and the C, get the K and C and other things, for example. Now notice that the mass, the imbalance mass, I call it M naught, okay? And the distance to the rotation center is going to called eccentricity. And this is turning. Now, I know it's kind of confusing. What the heck? What do you mean by M naught? So let's think about it like that. Suppose, just hypothetically, this is a propeller, the blades of a fan. Suppose that this unit is a fan, and consider the blades of a fan, a household fan with three blades. Okay, suppose one of the blades is broken, it's chipped off, and it's not there, or half of it is not there. So when you look at that particular component, that is not the fan itself. It's just the blade piece of the fan. In other words, the one with three blades sticking out, and you mount it on a a shaft that's turning. Now, the center of rotation, you know what it is. The center of rotation of the fan is that thing where the basically the shaft is coming out of the frame of the fan. But the center of mass of the blade is somewhere else. So this M naught represents the mass of the three blades with part of it is missing, and E is the distance of the center of mass of that broken thing to the center of rotation. So that's what I mean by mass imbalance. And this big M, the big M that you see here, is the entire fan with the broken blade and everything. Everything is big M. Okay, so now well, we just talked about this. So rotating unbalance, I just explained to you what I mean by that. Imagine a fan, one of the blades is broken, plastic, three plastic blades, one of them is broken, and the mass of that is m naught, and because part of it is broken, the center of mass may not be the center of rotation, okay? So here is the broken blade component. Three fans, one of them, or three blades. One of them is broken. So there is the blade. There is the blading system blades, and this is the other piece, which is m minus m naught, which is the actual fan. If I removed obviously m naught from it, then this is going to be m minus m naught. So the force is applied to this block whose mass is m minus m naught, because m naught, I'm looking at it as isolated here, okay? Now, first of all, if you look at the the mass imbalance right there is a force acting on it. We know that. There's a force acting on it, so in principle, up and down force. We know that. But the acceleration of that is the acceleration of the moving block up and down, and the fact that this thing is turning itself. So it has two components. One is because of the rotation of this blade system, or the mass imbalance, because of rotation of it, and the other one is because the unit is going up and down. So this is actually the free body diagram and the mass acceleration diagram of the unbalanced piece. Now, if you look at the machine, what are the forces that are acting there? Well, first of all, this Fr that is acting on that m naught, the opposite to it is acting on the block itself. Okay, right there, the mass itself. And there's a spring force, and there's a damping force. And because these bottoms are fixed, this is not a moving base, it's just kx minus kx and cx naught in this direction. So this is the free body diagram of free body. This is the free body diagram of the mass itself, and this is the equation. Sum of all the forces equal to mass times acceleration, and the mass, by the way, is m minus m naught, because I've isolated this. So whatever is left is m minus m naught, and all the forces Fr up positive, kx down negative, cx dot down negative. Good. Now, if you take this Fr and stick it in there, take this Fr, and stick it in that expression and clean up, this is what you're going to get. Just believe me. If you take this Fr and stick it in there, two things will cancel. Two things, one is positive, the other one is going to be negative, and that's what you're going to get. Great. Now, this is just written again. These are the same equation, no particular reason, it's repeated. Now, This mass, which is turning, it's vertical displacement. Vertical displacement is just E times sine. See that? This is the vertical displacement. See that? This is XR right there in that triangle. In that right triangle, there is E, there is XR, and there is E. This is the XR that we want. Yes, this is the XR that we want, and this angle is omega t. So right there, in this right triangle, XR is E sine of omega t. And I need the second derivative of it here. You can see that differentiate it twice. You're going to get this, plug it in, and the mother of all equations, F naught constant times sine omega. And I put a R there to remind you that this is a rotating plot. But that's the driving frequency of this rotating component. So remember, I said that the very first thing that we did, namely a mass spring damper system subjected to harmonic load, is going to be very important because the very common applications that we have is a base movement, base excitation, and rotating unbalance. And they both look the same. F naught, think about this thing as F naught and sine of omega t. So that is the end of the lecture today. Now we're going to look at this rotating balance along with quite a few examples on Thursday. All right, guys? And good luck.